Hello, welcome to today's problem solving session. Uh, we're looking at the geometry problem I proposed some days back. And we're looking at two different solutions to this. So the first one is based on a geometric construction, which is kind of unique to the setup of the problem. Okay, so it goes like this. Let ABC be a triangle with right angle at B, so as shown in the diagram. And suppose there exists a unique point D in the interior of triangle ABC, such that we have the blue angles equal, and then we have this length criteria. So I want to show that these lengths are in geometric progression. All right. So to do this, we're looking at a construction. So solution. All right. So I'm just gonna make a sketch. Okay, so what we're going to do is this is point C, ABC, right? So we are going to take a reflection of the triangle. So normally we have this at D somewhere here. So D. Okay, so if we connect this angle here is the same as the angle up here. So if we take the reflection, let's call this O. Take reflection of this figure across line. So reflect across OC. Okay. So if you do that, A becomes A prime, B becomes B prime, and the line AC will become this A prime C. And we'll also have this angle equal. This will be right angle. So in fact, AB, B prime, A prime is just a rectangle. And we have some lengths. So all this equal. All right. So from this angle condition, we see that if this is like alpha, then this will be, or let's say theta, then this will be theta, and this will be 90 minus theta, based on right angle triangle A prime C B prime, and that means the angle left here would be 90. Okay, so if you look at that and we connect A prime D, then looking at the condition we're given, so I'm just going to write the condition here. So we have a 3bc squared is cd squared, da squared, and ab squared. So we're just going to do a little bit of a trick here. So we're going to add bc squared to both sides. So this will be 4bc squared, and then we can write it this way. And then we have this plus this plus ab squared plus bc squared. Now ab squared plus bc squared, that will just be equal to by Pythagoras Theorem, ac squared, since that's right angle triangle, and by the reflection is the same length as a prime c squared. So now from this right angle we just got angle at C. It means we can actually add the first one on the one we just got to give, using Pythagoras theorem once more, to give the new hypotenuse, which is a prime d squared, and we have this. So if you observe this very well, you see that 2bc, which is also equal to this, will just be the length b prime bb prime, which is equal to a prime, as that's a rectangle. Okay, so once we've done this, then we can write it this way, and we can see that this is just a Pythagoras theorem all over again. So this simply means that the angle at, so this would be a prime will be hypotenuse, meaning the angle at D should be right angled. So if we join this should be 90. And so since this is 90, it means if we draw a circle, so yeah, so if we draw a circle centered at O with diameter a prime, then D will have to lie on that circle. So let's call this circle gamma. So D must be on the circle gamma. And conversely, if D is so we have two things, D on this line, so call this line L. So D is on L and D is on gamma. And conversely, if D is a point on this line and on that circle at the same time, then from the circle, once again, we get this Pythagoras theorem, and this will still hold. And from the other triangle, would have so we're going to get this is also 90 already, because of the line L is already perpendicular to A prime C, irrespective of which D we're picking. So we can still use the Pythagoras theorem as we did here, connecting these two. So we can break it apart as well. So every of this step can actually just simply be reversed. Once again, once we get A prime C, it's the same as AC by the reflection, which still holds, and then that's just AB squared plus BC squared, and take the square root of that. So we get back to this formula. So it means that whenever a point satisfies both of these conditions, then is the point we're looking for. But now we want this point not just to exist, but want it to be unique, meaning that we only want this. So this is a line, and this is a circle. So one intersection of this line and this circle to simply be exactly one point, and that means that it must be tangent, because for circles there are three possibilities: either the line just passes outside, it crosses it at 2 points, or it is tangent. So this is the scenario we must be dealing with. All right, so I'll extend this. So this is tangent, call this E. Okay, so next we'll draw a line parallel with the sides of this rectangle, and it's going to meet A prime C at the point we call G, and it meets AB at the point we call H. Okay, so H is an important point we're dealing with, but we're going to prove that that OEHCG is cyclic. So that means it means that all 5 points actually lie on one circle. So to do that, we just we'll start from G, and it's not just cyclic, it has a diameter. So the diameter here is EG. Okay, so I want to show you cyclic with that diameter. So first know more about G, and then we'll use that to get the other points. Okay, so let me change color here a bit. So now the first thing we're going to do, since we know that CD or CE is tangent to our blue circle, that's gamma, it means that if we draw a line from the center to that point of tangency, it should be right angled with the line L. Alright, so connecting these two right angles here, we get that this is going to be also parallel. So OD is parallel to A prime C, and that means that O, so let me come down a bit, So we have that O D G A prime will be a parallelogram. Okay, so not just that, but at the same time it means that OA will be equal to DG, opposite sides of a parallelogram, and so that means OA is going to be DG, and OA itself is equal to OA prime rather is equal to AO. So that means we also have this parallel. So OA is parallel with DG and they're equal in length, so that's also another parallelogram. So we have OADG is also a parallelogram. So the bottom line is this is parallel with this. Okay, once we've had that, then next we will see that when we connect E and O, we'll observe that E is going to EA is also tangent with our gamma, that's a blue circle, and that's because EAO is right angled, right? So that's part of the criteria for the tangency at A. Okay, so that's EA is tangent and ED is also tangent. So as a matter of fact, it means that if we join OE, it's going to be perpendicular, and not just perpendicular, it's going to bisect AD. So more importantly is perpendicular to AD. So this means that since OG is parallel with AD, it means O is also perpendicular to OG. So we get right angle at O. Okay, and then clearly there is a right angle at C. So look at ECG, that is clearly a right angle. Alright, so we get this, and finally EHG is also right angled because of we have HG is parallel with BC, and they are both perpendicular to BH or BA. So yeah, as these two angles are equal, so they are both 90. So we get 90 at H. So this means that that means if we draw a circle with diameter EG, H will lie on it because of the right angle at H, O will lie on it, and C will also lie on it. So we get this nice circle. So we get this circle here. Yeah, and this is the important bit we're going to use to solve this problem. All right, so we have, let me just bring out the sketch a bit. So we have a circle, and we have, this is not necessarily diameter, and we have a structure like this. So this is E, this is H, this is C, this is O. So these are parallel, and this is cyclic. So this is going to be a cyclic an isosceles trapezoid. To prove that, we just do it quickly. So you see that this angle here is equal to this angle from based on this segment HC in this circle, and also since HE is parallel to OC, by alternate angles should be equal to this angle at C here. So it means that the angle at O and the angle at C that I've marked are equal, and so their corresponding segments would also be equal. So this means that OE is equal to HC. Okay, now going back. So OE and HC are equal. So these two are equal. So now if you take a look at triangle ODE and triangle CBH, they are going to be similar triangles because they are both right angle triangles, and also we can just use Pythagoras at this point. So OD and BC are already equal. So why OD is equal to this is because of OD is radius of the first blue circle, that's gamma. So it's also equal to AO, OA prime, and BC, and so on. So it's equal to BC, and then OE we just got to be equal to CH. So by Pythagoras theorem, the third sides would also match up. So we get this is equal with this. Okay, we're almost there. And not just this, we also have that since OD is parallel with A prime C, then if you extend OD to meet BC at some point, you're going to get a parallelogram from OA prime C, and we expect the length here to be equal with OA prime, and so that has to be exactly with B. So this just simply means if we extend this line, it actually meets B. So OD B is collinear as they form a straight line. Okay, so with this now we have the right tools to look at ratio. Okay, so the ratios will be based on theta. So look at I'll pull that section of the triangle out. So we have this, and so this is D 90, because this was collinear with O right there. So this is C, this is A, this is E, and this H. So H. Okay, so this angle here, theta, just chasing some angles quickly, you get theta here as well. Parallel gives theta here, and this is also theta. And we've gotten that this length here is equal to this length. So all these triangles are going to actually be similar because they're right angle triangles with angle theta. And if we draw just such a triangle, and we call this length x, and call this alpha x, where alpha is now the tan ratio, and this is theta. Okay, so if we do that and we start our x, let's say from here, then this should be alpha x, and similarly this would be alpha times that, so this would be alpha squared x, but that is equal to ED, which is what we just showed. So that's the yellow segment in the previous diagram. So these two are equal, so we get this nice figure. So this part here would be alpha squared this. So they're going the ratio, similar ratio, so we just multiply each time by alpha to get the next sides. Also, by Pythagoras theorem, we'll get this raised to the power 4 be equal to this plus 1. So as a matter of fact, alpha squared is just going to be the golden ratio. Okay, so once we have this, basically we are done. So how do we conclude this? Well, we have CA or CA. So these are the length ratios we are interested in. CA, AB, square versions of this. BC, BC, we have CD, and then we have DA squared over 2. Actually, this is going to be equal to BD, but we're not going to focus on that. Alright, so for the first one, we see that in triangle ABC is just similar to this triangle, and AC part is the longest one, followed by AB, followed by BC. So they are going to go in the same ratio. So the ratio here is if you take the ratio, that is going to be alpha squared. We take the same ratio here, it's also going to be alpha squared. Now in BC and CD, they appear in triangle BCD, which is similar to the same figure, where BC is now the diameter and CD is the second longest side. So they also follow the same ratio, which is alpha squared. Then CD squared will go with the same ratio to DB squared, but we want to show this equality. Or more directly, we can just show that CD squared is equal to DA squared over 2 times alpha squared. Okay, so to do this, we just go back to some of the things we're given this problem. Okay, so we know that DA, so I have alpha squared over 2 here, so DA squared will be 3BC squared minus CD squared minus AB squared. So this is from the condition given in the problem, and if you do that, we see that CB or BC squared would be alpha squared times CD from the ratios we developed earlier, and this one will be alpha squared times BC, which is alpha raised to power 4 CD squared. So this, if you cancel out CD from everywhere, it just comes down to trying to prove this identity: 3 alpha squared minus 1 minus raised to power 4. But we have this relationship, so we can just use that to simplify the right hand side. We'll see that we'll get 1. So alpha squared over 2 is alpha squared minus 1, and that gives alpha squared over 2 2 alpha squared minus 2. So we can factor out 2 and cancel that out to get alpha squared minus 1, or alpha 4 minus alpha squared. And looking at the relationship once again, that's just 1. So that brings us to the end of this solution. Alright, so next, let's take a look at a more direct approach. So it's basically trigonometry. We're using just similarity, Pythagoras Theorem, and Stewart's Theorem. Okay, so solution. Okay. Since D has a lie inside, it makes sense that this angle, which we called theta before, it has to be less than 45. Okay, because if you add the 2 theta we have so far plus the 90, that should be less than 180. So theta is less than 45, meaning that BC should be the shorter side of this triangle. So we're going to draw it as such. Okay, so let's call this length here. So this is D, and this is what we called E earlier. So let's call this length A and call this length B. Now we have some similar triangles. So we have ABC is similar. So the angle at A is the theta, so that's a C. Angle at B is 90. That's a B. as well, and then E. So we have this similarity. So this means that AB over BC will be equal to CB over BE, and cross multiplying we get AB is BC squared. So BC is just going to be square root of AB, and from this we can use Pythagoras theorem to complete the remaining sides. This would be square root of B squared AB, and if you call this length CD x, then this length here would be CE minus x, and CE from Pythagoras once more would be square root of A squared AB minus x, and call this let's say P. Okay, so we know two things from the question. We know 3BC squared, which is 3AB, is equal to AB, which is B. So we have this squared, AD, which is P squared, and we also have CD, which is x squared. So P squared is just 3AB minus B squared minus x squared. And also we use Stewart's theorem on triangle AEC. Okay, so I'm just first going to write the theorem, which says that AD squared plus ED times CD times entire length CE is going to be equal to AE squared times CD plus AC squared times ED. Okay, so this first one is just P squared, and then we have x times the other length times CE, which is just this length altogether. Okay, now AE squared, that's going to be, to get AE we subtract BE from AB, so that's B minus A squared. CD is x, AC squared is this, and ED is this side minus x. Okay, so now we're just going to get quadratic in x, so plug in P squared as 3AB minus B squared. So doing a bit of simplification, we get this. Okay, and that gives A squared minus 2AB plus B squared here, x, minus x B squared AB. Alright, so now we're just going to look at this as a quadratic in x, but we want this to have a unique solution. So we're going to look at this as need to check the discriminant, so just take everything to one side. So this is squared here. Okay, so we get 2 root A squared AB x squared, so that's the only x squared term appearing from here, so we'll take it over. Now for the x terms, we have a number of them, so we have A squared minus 2AB plus BC squared minus this, and then we also have x term here which multiplies with this to remove the square root, so we'll subtract that on the other hand, and then we have the constant term, so just take this times this and subtract it from the other side. We'll get this sort appearing on both of the constant terms, so bring it out. We have this from the one on the right and subtract the one from the left. Okay, so this can be simplified. We'll see that this gives minus 4AB and this gives 2B squared minus 2AB. So cancel out 2, we get we get this is equal to minus 2ab. After we cancel out 2, get this. So this is a quadratic that gives us the length we need, and we want this to be alright. So I want to solve this quadratic equation, but before we actually solve this, we should check the discriminant to make sure we get exactly one solution. So discriminant, that will be normally if you have a squared minus plus bx plus c equals 0, discriminant would be b squared minus 4ac. Okay, so going by that, we get minus 2ab as the coefficient of x squared minus 4 times the leading coefficient, then minus times the constant term. So we get this. So this is the discriminant, and that gives 4a squared b squared minus 4. So these are the same sort, so square root to cancel out, and we have this. Okay, here we can actually factorize it as a plus b, b minus a. Now a and b are lengths, so they are not 0. And for this to have a unique solution, we want the discriminant to be 0. So you can write this as 4ab, ab minus a times b, b minus a. So this, they are not 0, so we must have this to be 0. Since this is not 0, so this implies that 0 is equal to ab minus, now we can use difference of two squares to simplify this part. So we can write it as b squared is equal to a squared plus ab. Okay, so if a is 1, now this would just be the golden ratio again. So b over a is actually just the golden ratio. You can write it as like this. So but the second term first, and then this one. So b over a is actually a golden ratio. Alright, so now just remains to prove the right question. Now we have what we need. Before we do that, we also find x. We'll find x, and then we'll find p. So to get x, now this is going to have a unique solution. So it's going to be a perfect square, or we can factorize it as a perfect square. So as a matter of fact, the a squared plus ab in those sorts here, they're actually b squared. So each of these will just be b if you take the square root. So we get bx squared minus 2ax plus. Now this part we can see that is equal to a squared using the same relationship here. So this will just be a squared b, and we can bring out b, and we get this squared. So it means that x is a, and then p squared, we can recall we got p squared before up here. So p squared is 3ab minus b squared minus x squared. Now x squared is a, so this is what we have for p squared, and plugging in what we have for b squared is a minus a squared minus ab minus a squared. So that's a 2 ab minus 2a squared All right, so with this now we have the major components we need. So once again we come back to the problem. This one, so CA squared, so CA was the biggest hypotenuse, which was B squared plus AB. If you take the square root out after squaring, AB was just B, so this is B squared. BC, if you remember, is root AB, so this is just AB. Now CD is X, which is A squared. So now DA is P squared over 2, which is AB minus this. So I want to show that the ratios here are all the same, so we just take the ratios. So let me just do this directly. So just want to check that these ratios are actually all the same. So most things will cancel out. Here we have this B over A, B over A over B minus. So this one actually is already equal. For this one, to see that they are equal, we just cross multiply, and we'll get this relationship. If you remember this relationship, so we'll get this again if you cross multiply, and the same actually applies here. So you're going to get B squared, cross multiply, get B squared minus AB is equal to A squared. So yeah, so the ratios are all hold. That brings us to the end of this method as well. Alright, so that's the end for the video. Make sure you like and subscribe if you've not done that yet, and drop a comment. If you have any questions, you are free to ask as well. Alright, so see you in the next one. Bye.